Okay, hi everyone. I hope you guys had a good weekend. I know this weekend was a long weekend due to MLK, so there was no discussion. So I'm going to quickly walk you guys through the discussion in case you guys had any questions on the worksheet. Okay, so let's get started. Problem 1A. So we're trying to show here that X transpose AX is equal to that summation over the rows and columns, xi, xj, aij, where A is a symmetric n×n matrix and X is an Rn. So this is easy to show if we first expand it. So let's do that. X transpose AX. This we will first expand. Remember that AX is a linear combination of the columns of A. So let's write that out. So we're going to sum over these columns of Aij and each element, or the columns of A, which we will write like this. All right, so that's this AX product. Oh, let me just that. Okay. Okay, so now we'll add in this dot product. So remember the first element of this X, the first element of this vector X will be dotted with or multiplied with the first element in this vector. So remember this vector right now, it is still in Rn. So now we're going to multiply the first element of this vector with the first element of this Rn vector. So that's the first step. Let's just write that for now, I guess. So x1 times the summation of xj times the first element. So j equals 1 to n a1j. That's the first element of that vector. And this will keep going until we'll multiply each one of them, and then remember dot product, we sum them all together. So now we do times x and j equals 1 to n xj a n j. And now we can simplify this to a single, just sum this up with the summation. So I equals 1 to n xi times this product. And now we can distribute the xi inside this summation. Oh, sorry. The second summation, j equals 1 to n xi xj a I j. All right, and that concludes this first proof. Now let's do the second for B. Okay, so now we want to take the partial of that value with respect to x1. Okay, so this shouldn't be too bad because now we have the expanded form. So we know that this expands to this nice summation over here. So we have this formula over here. So now it should be pretty easy. So let's first think about where x1s come into the equation, because we don't care about any of the elements that don't have x1. Those will all go to 0. So the first place where x1 comes into the picture is, let's say, when I equals 1. So if I equals 1, then we have this summation, this internal summation with j equals 1 to n x1 times xj aij. We know I equals 1, so that'll be 1j. But we're taking the partial with respect to x1. So what does that become? Or let's write it on a separate step. So partial with respect to x1. Actually, no, let's just figure it right here. Basically the summation, we take the partial with respect to x1, so that disappears. Okay, and now the other place x1 comes into the picture is when j equals 1. So let's do that. At j equals 1, we can sum over the i's. So we said j equals 1, so it's xi x1 a I1. Yeah. Okay, and then once again, because we're taking the partial with respect to x1, that goes away. So at least so this worry about. Okay, so now we know that A is symmetric, so that implies that Aij is equal to Aji. So that gives us that A1j is equal to the same as AI1. So we can sum this all up in one summation with xj xj a1j, which I think is how they wrote it in the discussion. Yeah, okay, cool.